And out here in the wilderness, the chores don't just stop because it's winter. That's why I wear Willy Warm. They'll keep your 10 little tater tots toastier than any other gloves on the planet. And that's a scientific fact.
Tater tots.
Super tight with patented microfibers, so no cold air gets in. And best of all, they're thin, so you can grab stuff nice and easy. Willy Warm, the warmest gloves money can buy. I'll bet my ranch on it.
In fact, there is no ranch. Willie has fled the country with his customers' money. And worst of all, Willy Warm gloves are ice cold. According to business records seized by police, some 10,000 customers purchased these worthless gloves. That's a lot of Willy cold hands.
Our field trip to the mountains is next week. We spent our whole budget on these Willy Warm gloves, and now the board wants to cancel the trip because the kids' hands are gonna freeze. Do you think you can make us gloves that work?
I'm not a glove maker, but I'll do my best. First things first. We need to see exactly what's wrong with these gloves.
How's it fitting, MOSA?
Well, I'd like to say like a glove, but it's hitting every part of my skin. And thanks to the dense microfibers, I feel no air from the outside. Not even through my wrists.
Okay, goggles on.
MOSA, you're glowing.
Wherever there's red, it's heat. That's my natural body heat.
Whoa! It looks like the heat is moving right through the glove.
From high heat close to my hand to low heat out in the air. I think I'm done here.
Keeping cold air out didn't keep you warm. That heat went right out of your hand.
The cold didn't move at all. It was the heat that moved. We need to look exactly at how heat moves from one thing to another.
I think that might be happening right now. I put my spoon in my soup, and the spoon got hot.
Let's take a closer look.
Those look familiar. Molecules and atoms.
Right out of the pot at a high temperature, the particles in the soup are vibrating a lot.
Meanwhile, look at the spoon's particles, right at the tip where it's hottest, just moving a little. Let's get this party started!
I feel it, it's kind of a tingle, or maybe a shiver. Call it a tremble, ooh, call it a quiver.
Hey, quit bumping.
Oh, you feel it too?
Feel what? Oh, that. Yeah.
We're shaking and bumping and shaking.
Thumping
Bumping and quaking and quaking and thumping.
Heat, 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 heat,
All aboard the thermal energy transfer.
heat, 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 it's contagious.
Thermal energy transfer. So, the particles in the spoon conduct the heat by bouncing into each other over and over and over.
Those are some peppy plastic particles.
I wonder if it might work differently in another material.
Like clam chowder?
No, the same hot liquid, but a different kind of spoon, like metal.
It's definitely getting hotter than the plastic.
So some materials are better at conducting heat than others. I bet we'll find out why if we look up close.
Shaking and bumping and shaking.
The particles in the metal are closer together than the plastic particles.
And packed in so tight. Of course they're going to bump into each other more often.
One time, we combined our prom with another school's prom in the same auditorium.
So, the more tightly packed, or denser, an object's particles, the better it conducts heat.
What else could we test with bowl number 3?
Maybe not a solid this time. Let's look at how air conducts heat.
Shaking and shaking and shaking. Hey, y'all, get over here. I want to bump. Oh, shoot, there goes the party.
Air particles are much further apart, so they can't bump into each other and transfer energy as easily. Which means air, unlike metal or plastic, is not a good conductor of heat.
What's all this have to do with gloves?
Remember how the heat just went right out of my hand through the glove into the air? Well, if certain materials are better at letting heat out, maybe certain materials are better at keeping heat in.
You mean...
Something that would block thermal energy transfer. Something that would insulate. That's the material we need for our gloves. An insulator.
Metal lets the heat right through, but styrofoam blocks it better. A good conductor is a bad insulator.
Same here. Metal heats up faster than ceramic, but once it's hot, ceramic holds heat for longer. A bad conductor is a good insulator.
Great work. But ceramic and styrofoam don't make good gloves. I've polled 20 different species of animals about why their fur blocks thermal energy transfer. And my last stop is Portugal, home of the legendary merino sheep. Hello there. I've heard so much about your wool. Apparently, it keeps you warm and dry in the winter. Would you mind if I took a sample? No offense, but your wool doesn't fit tight like Willie's glove. In some places, it's not even touching my skin. Willie's fibers are dense, but yours, there's all this space between them, which seems like it would let heat out everywhere. Why not? Look closer. I just see fibers and a whole lot of little pockets of blank space between them. I'll take your word for it that your wool is a good insulator, but I still don't understand why. Thanks for letting me tag along. I've got 3 days to design a warm glove, so all pointers are welcome.
You're in the right place. Keeping houses warm is our job.
Why does each window have 2 panes of glass?
Insulation. 2's better than 1.
But why aren't they right up against each other?
It's the middle layer that counts. Heat from the inside makes it through the first pane of glass. Then it hits that middle, and it has nowhere to go.
What's in there? Clear insulation?
More commonly known as air.
Shaking and bumping, bumping and shaking.
Air is not a good conductor of heat.
A bad conductor is a good insulator.
I figured out why Willie's gloves were a flop, and why these gloves are going to keep your hands warm up in the snow.